Alright guys, sorry about the confusion on what the pages were. I blame that on trying to get things sorted out before hitting the pool on Saturday. Um, 69, I am going to do in class as an example for us before we have the worksheet. So page 70, here are your videos. Page 70, we're going to start moving from a discrete observation or discrete variable where we can sit there and write down every single possible outcome and actually make a list into a continuous variable. So for continuous variables, we can't write out these individual values. In fact, there's an infinite number of them. I mean, between 0 and 1, there's an infinite number of possibilities right there. So instead, we're going to use what's called a density curve to figure out our probabilities. So our density curve, we're going to be looking at the area under it to determine our probabilities. So those of you who are taking calculus, we're looking at integration, though we will not actually be doing any integration or calculus in this class. So the sum of all the probabilities, i.e. the area under the curve, is going to be 1. And the area under the curve for a particular interval is the probability of x being in that interval. So let's see what this looks like in a simple example. So the simplest example of a probability density function is the uniform distribution. So a variable that follows the uniform distribution has an equally likely chance of taking any value in the interval. Suppose that the time to complete a question has a uniform distribution between 0 and 5 minutes. What is the probability taking a student taking between 1 and 2.2 minutes? So this is what your curve would look like if you were making a curve. Our x's and our probability of x's look something like that. Now, a uniform distribution means every probability is equally likely, right? So we're going to make our probability straight. And this probability is going to go from 0 to 5 minutes. After 5 minutes, it drops to 0. It's impossible to take more than 5 minutes according to this question. Before 0, it's at 0. So the only area, the only curve that we have above or not at 0 is between 0 and 5, and it's all equally likely. Now we want to know about being between 1 and 2.2. Pretend those are actually where they should be. So this is the probability that our x is between these two values. Now, just to throw out here, it doesn't matter if I use greater than or equal to's or greater thans when we talk about these. This is the exact same thing because the area of the line itself is 0. So whether you include or don't include doesn't make a difference when we're talking about continuous variables, though it does make a difference when we talk about discrete, because including 2 is different than not including 2. We have another probability to add in. So it doesn't matter here. We can use whichever one we want. And we have two ways we could do this. One, we could figure out what proportion of the curve is being described here, or we can actually figure out where this probability density function exists. So we know the entire area of this curve for all of the x's, right? So we'll just go from 0 to 5. This entire curve has to be 1, right? And it's a rectangle. So we can easily figure out what this area is. We can see the base of our rectangle is 5. And the actual probability, whatever this is, that's our height, right? So I can just put this down as our h. So if I want to figure out what h is just 1 out of 5 or 0.2. That does not mean there's a 20% chance of taking 1 minute, 2 minutes, 5 minutes, because remember, each of these different values is a probability of 0 because there are an infinite number of possibilities between 0 and 5. So the probability of any one value is approximately 0. That's why we're only going to look at regions under the curve. So throwing that out there. Now that we know the height, we can figure out the area of this curve. We know its height is 0.2, and the base, well, to get from 1 to 2.2, this is 1.2. So the probability of being between 1 and 2.2, that's our base times our height, which is 0.24. So 24% chance of taking that amount of time. And I also could have done this just how much of this whole rectangle are we talking about, right? This is 1.2 out of the 5 possibilities. Same thing. So that's the uniform distribution. I have definitely asked test questions about it in the past. I've asked questions that involve a triangle. Basically, what these questions come down to is just realizing probability is equal to area under the curve. As long as you know that, you should get any test question about that correct. Now, the normal distribution is our most famous of these continuous distributions. Remember, when we say something is normally distributed, that means it is symmetric, unimodal, and bell-shaped. So, if we have something symmetric, unimodal, and bell-shaped, we know the whole area under here is 100%, right? For the entire thing, not just that little section. And in fact, we know the empirical distribution as well, the empirical rule. So we could actually talk about that 68, 95, 99.7. In fact, that's what's on page 71 because apparently I moved it there and then forgot and taught it to you guys before. So we'll probably just skip pages 71 and 72. But what we do want here is we do have some squiggly line notation. We saw this with the binomial. This squiggly line notation says that x follows. That's what the squiggle means. And the n stands for a normal distribution. And if you know the mean and standard deviation for the normal distribution, you know everything about it. So this is our notation. The standard normal, this is our z-scores. They are also normally distributed, but centered at 0 with a standard deviation of 1. So just some new notation. The one thing we might want to know about is this. After that, we have the empirical rule questions. Again, I don't really care too much about these. And then we can start getting into the standard normal, which is the next video. So that's it.